Continuing on with Chapter 7, we are looking at reaction mechanisms and rate equations. A good mechanism is a worthy goal because it allows us to understand the chemistry better and perhaps to predict how to control a reaction better and how to design new experiments. One of the important guidelines of kinetics is that products of a reaction can never be produced at a rate faster than the rate of the slowest step. If one step in a multi-step reaction is slower than the others, then the rate of the overall reaction is limited by the combined rates of all elementary steps up through the slowest step in the mechanism. Often the overall reaction rate and the rate of the slow step are nearly the same. If the slow step determines the rate of the reaction, it's called the rate determining step or the rate limiting step. Imagine that a reaction takes place with a mechanism involving two sequential steps, and assume that we know the rates of both steps. The first step is slow and the second is fast. Here we have elementary steps 1 and 2. It tells me that the first one is slow and the second one is fast. Our first step, we have A plus B, so it's bimolecular, and it forms X plus M. M must be our intermediate because it does not appear in our overall equation, and M comes back down here to react with A, another A, to produce Y. So we have Y and X as our products, and we have two A's plus a B. Almost as soon as M is formed, however, it's rapidly consumed by reacting with another molecule of A to form that second product Y. The rate determining elementary step in this example is the first step. So the rate of the first step is equal to the rate of the overall reaction. We would write that then as rate is equal to K1 times the concentration of A times the concentration of B, since that was my first step. It's my slow step, so rate is equal to K time, and in the forward reaction we label that K1, A times B. M is a reaction intermediate, like we said. It does not appear in the equation describing the overall reaction. They usually have only a fleeting existence, but in some instances have long enough lifetimes to be observed. Let's look at this pretend chemical reaction. Step 1, 2, and 3. So there are 3 elementary steps. The species that cancel out are the reaction intermediates. In this case, we can see that A2B2 are reaction intermediates. A2B are reaction intermediates. And it looks like that is it. Each step is called an elementary step, and the number of reactants is called our molecularity. We have 2 AB reactants, so that's a bimolecular. We have one of those and one of those, that's a bimolecular. One of those and one of those, so they are all bimoleculars. These elementary steps are labeled slow, fast, fast. The slow step is our rate determining step, so that would be the first one. Therefore, we would write our rate law as rate is equal to K times the concentration of AB, and we would square it because there's 2 of them. The rate law is not based on the overall reaction. The overall reaction rate law would be K times AB squared times C2 squared. It is not based on that overall reaction. It's based on the slow elementary reaction. Consider the following reaction. We have 2NO2 plus F2 to make this product. If the reaction proceeded by the overall reaction, the rate law for the reaction would be third order overall. 2 plus 1 would be 3. The actual rate law was found to be this. That indicates that there must be more than one step in this reaction, and the slowest step in the mechanism is a bimolecular reaction between NO2 and F2. Let's look at a proposed mechanism. The first step, possibly the slow step, would be when we would take one NO2 and bombard it with an F2, giving me an intermediate, F, coming down here, and then bombarding it with a second NO2 to give me my second product. So I would get 2 FNO2s. This is the slow step. Then I would have my rate equal to K times NO2 times F2. That would be my rate, which is my slow step. Let's look at this example. Oxygen atoms transfer from NO2 to to CO produce nitrogen monoxide and carbon dioxide in this reaction. The mechanism for this reaction depends on the temperature, with one mechanism followed at low temperatures and another followed at high temperatures. The rate equation for this reaction at temperatures less than 500 is this. Can the low temperature reaction occur in one bimolecular step? Well, obviously not. If our rate is equal to NO2 squared, then that would be NO2 plus NO2. And we're somehow missing that CO, so there must be a slow step involved. Here would be one proposed mechanism. If I have two NO2s bombarding with one another to form an NO3 and an NO, and then that NO3 was an intermediate, came down here, and then bombarded it with the CO, then I would have a product of NO2 and CO2. So one of those NO2s and one of these NO2s would cancel out, leaving me with just one NO2, bringing down that CO. The intermediate cancels out, and then I'm left with one NO down here and one CO2. So the slow determining step must include two NO2s bombarding with one another in the slow step. Let's look at this reaction. A proposed mechanism for producing hydrazine is this: 1, 2, 3 steps. What is the overall equation? Which step of the three is rate determining? Write the rate equation for the rate determining step, and what reaction intermediates are involved. Pause the video here. I'm going to answer B first. The rate determining step is going to be step 2, this guy. The rate equation for this, we would say the rate is equal to K times the concentration of NH2Cl times the concentration of NH3. Let's look at reaction intermediates next. Let's see who can cancel out on the right and the left side. I've got an NH2Cl that can cancel, N2H5 pluses that can cancel, I have an OH minus that can cancel, and I think that's it. Let's bring down everything else. I have two NH3s plus an OCl minus, and that's making N2H4, H2O, and Cl minus. These three would be my products. I just don't have room to write them. There we go. There is my overall reaction. The second step is our rate determining. That would be my rate equation for the rate determining step. And those are all of my intermediates.